All right, good afternoon, everybody. Thank you for coming. I'd like to introduce Ned Batchelder, who's going to talk about getting started with testing.
Hello, everyone. So this talk starts at 1:40, but the printed program says 1:55, so there's going to be some people coming in late, and you can all make friends by palling up with them later and explaining what they missed in the first 15 minutes. I'm going to have a lot of code on the screen. It might be difficult to read. Your two options are to move forward or to use the bit.ly URL at the bottom, which will take you to a page on my website which has all of the slides and the code, and even the text if you want to follow along. So my goal here today is to show you a way to test your code. I'm assuming that you have not written tests before, and you are test curious, let's say, and that you want to figure out how to do it. So I'm going to show you a way to test code. There's lots of different ways to do it, and if you talk to testing experts, they're probably going to tell you that this is all the wrong way to do it, maybe, but this is a way to get you started. I want to remove the mystery from writing tests. First, a little bit of philosophy about this. Why test? Testing, automated testing, is the best way we know to figure out if code works. What I'm trying to show you in this talk is a way to look at tests as a solution to a very important problem that you have. You have written some code, and the problem you have is that you don't know if it works, and tests are the solution to that problem. Some people approach tests as a check-off on some sort of form that they need to complete before they can go home at the end of the day. It's just sort of paperwork to get done, and that's the wrong way to look at it. You'll be very unhappy if you write tests that way. Testing is a very serious problem it's a serious solution to a very serious problem, and if you approach it as such, as real engineering, you'll get a lot of benefit from it. It will save you time because you won't have to go back and fix problems later, and it will give you better code because the tests will actually help you write better, more modular code to begin with. Most importantly for me, it removes fear from the development process. If you've ever approached a large piece of code and had to change it and thought that you were certain to fuck things up and make the code not work anymore, testing is a way to make sure that you will not do that anymore. It turns fear into boredom, is a way that I've heard it put. And the other way to think of it is that debugging is very hard, but testing is easy. So testing is a really good way to write really good code. This is most developers' first impression of testing. They know that they should be doing it, but they're not doing it, and so they feel bad. And just like our poor developer here, they're paralyzed by this feeling of inadequacy and uncertainty and doubt about what they should be doing, and they feel bad. And I don't want you to feel bad. Testing is hard. It's a lot of work. People, and by people I mean you, will not want to actually do it, but it pays off. So if you approach it as an engineering task to solve a problem that you really have and that you want to solve, it will work out for you. The reality is that the universe is a chaotic place. So here's another poor developer. She recognizes that the universe is full of chaos that is trying to attack her code. Okay? You know how it is. You write a program, it seems to work great, and a week later, who knows what's happened to it? Some gremlin has gotten to it and it no longer works. Tests are the defense against this. Our developer here has a spear and a shield. Those are the tests, and I'm going to teach you how to write them and use them. All right, our goal for this talk is to get these two developers happy and confident at the end. So the roadmap, there are three main parts that we're going to talk about today. The first part was we're going to grow some tests organically. We'll take some real code, and we'll just start testing it sort of ad hoc, making up as we go along and talking about what we like and don't like about the way those tests are coming out. And then the main piece of the talk is talking about the unit test library in the standard library. That is the right way to write the tests. And I'll show you some bits and pieces of the unit test module and show you how to use them to build your tests. And then I want to get into a kind of an advanced topic, mocks, which is something that you don't often see in a novice talk, but it's a really, really powerful tool for making your tests much more powerful and flexible. So let's start from first principles and grow some tests. So here is our stock portfolio class. And again, if you can't read the code, there is a bit.ly link at the bottom, bit.ly/pytest0, where you can see the code. So this is a stock portfolio class. It's very simple. We define a class. It keeps a list of tuples, name, shares, price. You can buy some shares for a certain amount, which will append that stock lot to the list. And then later you can ask, what is the cost of the portfolio, the original cost, which is simply the sum of the shares times the price for all of the stocks in our portfolio. Very simple code. How do we test it? Well, the first test is, excuse me, you just launch the interactive interpreter and you start filling around with it. You make an empty portfolio and you can see that its cost is 0. And then you can buy 100 shares of IBM stock and you see that the cost is gone up. And then you buy 100 shares of HP stock and the cost has gone up some more. So this is really good. So the good thing here is we're testing our code. Let's be honest. There are developers who have not gotten this far, right? So right off the bat, let's just congratulate ourselves that we are actually testing our code. But the bad thing is that this is not a repeatable process. If we change the implementation, we're going to have to go and do this again, and we won't remember what it is we tested, and we'll probably miss a case, and that's where the bug will be. It's also labor intensive. You have to type this out every time, and you don't know if it's right. You're going to have to get out your calculator and see if the arithmetic works out right. So let's fix some of those problems. The second test, we'll write a Python file, and we'll import our portfolio class, and we'll basically do the exact same things we just did in the interactive interpreter. We'll print out what the cost is of the empty portfolio, and then after we buy 100 shares of IBM. And that's good, and we can see that the price has gone up for the IBM stock, and then after we buy the HP stock, it goes up. So that's good. We're testing the code. It's now repeatable. We can run that Python file anytime we like. It's very low effort. It doesn't take much to run that file, but we still don't know if it's right. We have to look at that output, and is it right that it comes out to 21263? You have to get out the calculator again. All right, let's add some more to our tests. So now here what we've got is a portfolio cost where we print out what it should be, and then we can print out what it should be, and we can print out what it should be, and here we can see that it's printing those results. I apologize for this code going off the side of the screen. Now it's even better. We've got repeatable tests with low effort. We've got it's better because we've got explicit expected results. We still have to check the results ourselves. Here the line of code. If it were wrong, we'd just have to look and see if the two numbers were the same or if they were different. Right? The computer isn't telling us whether the number was right. It's just showing us the actual result and the expected result. So again, let's add a little bit more to our tests. Keep in mind, these are not the way you're supposed to write tests. Okay? This is you exploring the problem of writing good tests. I'm going to show you with unit tests how to do this the right way. But here now what we've done is we've taken our cost, and in addition to printing a message about what it should be, we use an assert statement to assert that the cost should be 0. If you haven't used the assert statement before, it takes a condition, and if the condition is true, it simply carries on executing the next statement. But if the condition is false, it raises an exception. So here we can make an assertion that the cost must be 0. Because our tests are passing, the assertion never happens. So now we have repeatable tests with low effort, we have explicit expected results, and the results are checked automatically. Good. The problem is that if the test fails, it will actually throw an assertion error, and the tests will stop. This blue code is actually incorrect. There should be an assertion error there. So if one of those assertions fails, the entire program will stop and you won't run the rest of the tests. So if this were a real program that were doing many tests, you'd have 100 or 1,000 or even 10,000 checks to make. If the second one failed, you'd never find out about the rest of them. What we'd really like is for each check to be run completely independently. So, as you can see, this is getting complicated, right? If we wanted to approach that problem of how do we make the tests run independently of each other, that would be yet more engineering to put into these tests. That's going to grow. It's going to become a real program with real engineering. Typically, engineers, when they find that they are encountering problems that other people have encountered, they go and find a library to help them solve those problems. That library is unit test, and we'll get to that in a second. But first, let's talk about the characteristics we want from tests. We want our tests to be automated so that they'll be low effort and they'll be repeatable. Because if they're too hard to run or if they're too confusing to run, you're not going to run them. We want them to be fast for the same reason. We want them to be reliable. Remember, the point of a test is you want to run it and have it tell you something you don't know. If you doubt the test, then you haven't really gained anything. Now you've simply moved the question from does my code work to do my tests work? And you haven't really solved anything. So you need your tests to be reliable. You need to believe them when they say that something doesn't work. And when they tell you it doesn't work, you'd like them to be as informative as possible. Because if you think about the workflow is you run your tests. And if any one of them fails, you're going to immediately try and figure out what is broken in your code. And so the more clues you can get from your tests, the better off you're going to be during that debugging exercise. And lastly, they should be focused. Your tests should exercise as little code as possible, which is a little counterintuitive. Usually we want any line of code we write to do as much as possible. But with tests, we want each test to be as focused as possible. Because if it fails and you dive into your code to debug the problem, the less code it runs, the more narrowly focused your debugging task is. So this is what we want out of our tests. And now we can talk about how unit test actually gives us these properties. So unit test is a module in the Python standard library. It is the infrastructure that you use for well-structured tests, and it is the lingua franca for tests. It is based on the same patterns as JUnit and NUnit and CPP unit and a lot of testing libraries across many different languages. For that reason, unit test has kind of a Java flavor to it, which a lot of people, Pythonistas, don't quite like, which is why there are alternative ways of writing tests. But we're going to talk about unit test here because it is the way everyone starts out writing tests, and all the test runners and test tools support these tests. So this is an actual unit test. To write a unit test, and by unit test, by the way, I just mean an automated test. You import the unit test module, you import your code that's under test, and then you're going to define a class. And your class is derived from unittest.testCase. So all of your tests will be in a class that derives from test case. And the tests themselves will be methods in this class that start with the word test. So here we have a method called test_by_1stock. And it's going to do the test that we did before, where we make an empty portfolio, we buy 100 shares of IBM, and then we can make an assertion that the cost is what it should be. The way you run tests with unit test is that you use Python-m unit test. If you haven't seen the -m flag, it means instead of running Python code that you find in a file I'm going to name, you're going to run Python code in a module I'm going to name. And so by running the unit test module as your main program, it knows how to actually take the next argument, test port 1, import that, and find the tests in it. So it will automatically find the test class and the test methods and run them. This single dot means that it ran one test, and then it tells you that it ran one test, and everything went okay. So that ran your test, and the test passed. Behind the scenes, what actually happens is unit test instantiates your portfolio test class to get a test case object. And then it runs the test method inside a try-except block. If it got an assertion error, if your assertion failed, then it records a failed test, but otherwise it records a success test. So conceptually, it's very simple. And this is perhaps how you might have approached the problem if you were building on the earlier examples and trying to solve this problem yourself. Wrap each assert in a try-except and catch the assertion error and print something out if it failed. But unit test will do all this for you. All right, let's add some more tests. So here, of course, there's more conditions that we have to test. So we'll also test the empty case. The portfolio should be 0. Here's the buy one stock that we had before, but we'll also test buying 2 stocks. So we buy 2 stocks and assert the cost as that. Now you see we have a ... That ... is not me leaving things out of this code example. That is literally 3 dots that unit test prints, one's for each test. You get a dot for every passed test. Some people who are really into tests talk about being dot addicted, that you just want to see lots and lots and lots of dots. Because every dot means a test that passed. And then it tells you that it ran 3 dots, and it tells you that it went okay. Under the covers, what happens again is it makes a test case object, and then it runs a test method, and then it makes a whole new test case object to run the second method, and then it makes a third test case object to run the third method. This is a very different way of using classes. Usually with classes, you make one object to represent a thing, and then you call many methods on it. Here we're going to make a class that has many methods. Each method gets called once on a separate object from every other method. But you can see this gives us test isolation. So not only do we have a try-except blocker out in every test method, so they run independently, but because each one of them is running in a brand new test case object, it's very difficult to do anything in the first test that's going to affect the outcome of the second test. Test isolation is all about making sure that every test is independent of every other test. If you do something in test 1 and it passes, but its side effect is visible in test 2, how do you know that test 2 is really testing what it's supposed to test? So the idea is to keep the tests independent of each other and to make sure that failure doesn't stop the next tests from happening. So we keep them all completely isolated. In theory, you should be able to have a 10,000 test suite and be able to run any single test out of it all by itself and have that test pass just as if it were run along with all of its 999,000, however many it is, brothers and sisters. It's hard to do arithmetic on stage. Now, what does failure look like? So suppose we had either broken our test code or broken the product code itself. When you run the tests, you'll get, instead of a dot, you'll get an F. The F means failure. Okay, so here what we've done is we had an assertion that was wrong. We had the wrong price in there or something, and it raises an assertion error. So what happens is all the tests run, and you get an F for every failed test and a dot for every passing test. And then at the end, every failed test prints a stack trace. So you get a full stack trace. It's not printed when it fails, because that would interrupt the whole field of dots thing. So you get all of the dots and Fs, and then you get all of the failure tracebacks. And those tracebacks are very useful because that's part of the debugging clues that helps you go and find out what product code has failed. So this is better because the failed tests didn't stop the other tests. But it's bad because we don't actually know exactly what failed here, right? We can see that the cost was not 17,648, but we don't know what the cost actually was, right? It could have been 0. It could have been 17,649. We don't have that information. So instead of using an assert statement, unit tests.test case objects give you methods called assert equal, for instance. So here you can see that we've got our test by one stock method. And instead of using an assert statement, we've called a method on the test case object itself. And instead of using an equality operator, we've passed the two values into assert equal. So this is kind of stylized compared to what you're used to, but the advantage is that when the assertion fails, it can actually print out the value it got and the value it expected. So we can see the assertion failed because 17,600 is not equal to 17,648. And that's a clue. 17,600 is the thing that went wrong. Now we have a piece of information that can help us diagnose and debug the problem. So the unit test module gives you a lot of assert helpers, assert equal and not equal, assert that this is true, this is false, that that is in that this is almost equal to that for floating points, et cetera, et cetera, et cetera. Regex matching, all sorts of interesting assertion helpers for you to write your tests in a way that the test runner can give you lots of information. One pro tip that large projects often get to, but people rarely do at the very beginning, make your own base class to derive all your test cases from. So here what I've done is I've created a class called portfolio test case, derived from test case. It doesn't have any test methods in it itself. A test method, remember, starts with test underscore, but it has this helper, assert cost equal. And here, instead of passing in two numbers to assert equal, I can pass in a portfolio and a cost, and then this method will assert that p.cost is equal to the number that was passed in. And so now I've raised the level of discourse up into my own domain. Instead of writing tests that assert two numbers are equal, I can write tests that assert that the cost of a portfolio is equal to something. So here I can say assert cost equal of p is equal to 0. And I still get the nice assertion because I'm using assert equal under the covers, and I get the assert cost equal method because I've derived from portfolio test case. These base classes tend to grow over time, and especially if you're focused on that kind of base class, then you have an opportunity to write really good domain-specific helpers. For instance, it's very common in web testing to say, I got a response back. I want to assert both that it is a 200 response, it's successful, and that it has this word in it. Well, why not just have a method that says assert word in response, and do the 200 check in there as well, and you can have one line in each of your tests rather than two, because your helper method has taken on some of that domain-specific knowledge that you're going to use over and over again. This is one of the things I notice about tests, is people approach them as rote boilerplate rather than code to engineer as if it were really code you cared about. You're allowed to refactor your tests and move common pieces into helpers and functions and classes to help you build those tests. By the way, there's a third possible outcome besides dot and F, and that is an E, and E happens if any exception other than assertion error comes up. So here, for example, you see that for some reason in our test we called this by XX method, which doesn't exist. It doesn't have that attribute, so it raised an attribute error. That test ended with an E. And the reason that's distinguished is a good test should either successfully pass or it should fail in an assertion. If it fails in some other way, that really means that the test dropped the ball. Right? The test should have a thing in its hands and say, it failed or it succeeded. But if another exception happened, then something is truly wrong with your test, and you have to go and fix the test. By the way, this brings up one tricky thing for beginners, which is negative testing. Let's say you want to call a function method, and you want to test that it raises the exception you expected. You can't just call the function. Here we are trying to call the by method with the wrong number of arguments. So it should raise an exception. If we wanted to test that, we can't simply run this test method this way, because that will actually raise the exception. We'll actually get an error result because the type error will be raised by the by. Type error is exactly what we want to happen, but we haven't managed to assert that the exception happens. We've simply managed to make the exception happen. Unit test has a way to do this. There's a self.assert raises method that you can use as a context manager in a with statement, so that you can put the p.by line into the with statement, and you can assert that it raises the type error. And that with statement will catch that exception for you, and it will check that the exception was actually the type error that you expected, and the test will pass. Let's test add another method to our portfolio class. We're going to add a sell method. So the sell method is going to take a name and some shares, and it's going to find that holding, and it's going to subtract that many shares from the portfolio. To test sell, we're going to make a portfolio. We're going to put some things into it. We're going to try to sell 50 shares of Microsoft. This cost should have gone down. If we try to sell Microsoft, but we're trying to sell more than we had, it's going to get a value error. If we're trying to sell IBM and we haven't even bought IBM, we're going to get a value error. But notice there's a lot of repetition here. And again, just like any code that you write, if you see repetitions, if you can squint at code and you can see a repeating pattern, that means that there's stuff that you can refactor. And the same is true of your tests than of anything else. Just because you feel like your tests are boilerplate, that doesn't mean they should be boilerplate. You should make them as expressive as possible. So we want to refactor all that code out. Luckily, the unit test gives us a way to do this. A class can define a setup method, and the setup method is invoked before each test method. So here the setup method is defining a self.p, which is a portfolio object, and we're going to buy the 3 stocks we want to buy. And then within each of our test methods, we can simply access the self.p that was created by setup. So here we can have much shorter tests that are much more descriptive of what they want to do. What's happening under the covers is that for each time that we create a test case object, we're going to call the setup method. By the way, it could fail and give you an E output. But if it succeeds, we'll call the test method. We'll record the failure and the error and success as always. And by the way, there's also a teardown method that will get invoked at the end of all of your tests to clean up whatever the setup did. We didn't need one for the previous example because it was just creating in-memory objects. But if you were creating files on disk, you could clean them up in the teardown method. So setup and teardown also give us a great way to create isolated tests. They establish context, they are a place for common pre- and post-work to live, and they give you isolation even with failures. And as a pointer off to something else to look at, if you find yourself creating lots and lots of big common data, you want to look into a thing called fixtures, which is a term of art in testing, but it's also the name of a Python library. Again, tests are real code. You're going to have helper functions and classes. They can become significant. And by the way, you're going to write tests for your test helpers because you want to know if your test helpers are working so that you can trust that your tests are working. And you should not resent that. That is a good sign that your project has grown to a level of maturity and a level of testing that you are a really good software engineer. So pat yourself on the back. All right, let's talk for a bit about mocks. As I mentioned before, it's really important for your tests to test small amounts of code. The less code each test tests, the more narrowly focused your debugging task will be when that test fails. But we always build systems so that components depend on each other, right? We're all used to building these towers of abstraction so that at the top level, you've got all these things you're depending on, right? How can you test just one component in your code? Dependencies in your code are good because you're building on the work of others, but dependencies in tests are bad because it puts more suspect code in each test. In addition, some of those components might be slow, and remember, we want our tests to be fast, right? The problem with testing missile launching sites is that if your test really launches a missile, that takes a long time. You want your tests to go fast. Not only that, but your tests might be unpredictable, right? If you have a flaky component that isn't really the focus of your test, you want to get it out of the way so that you can test the code that you do want to test. This is the way systems are often built with a code under test is depending on all these modules. What you want to do is you want to replace those big components with little pieces so that you can reduce the amount of code in each test. Let's add a little bit more to our portfolio. Stock portfolios are only interesting because stock prices go up and down. So let's add some code into our portfolio that's going to actually go out and talk to finance.yahoo.com to get the actual price right now of our stocks so that we can find out what the current value of our stocks is. So this value method is very cool. We can actually buy some stock and we can actually get the current prices for IBM and HP stock and what our current value is. Now think for a minute about how we're going to test this code. We cannot write an assertion that says, I assert that IBM is trading at $100 right now, because we don't know what IBM is trading at. That's the whole point of this code, is to get information that we don't have. How do we write a test that tests that this is working properly? Right? It's live data. It's unpredictable. That's its entire point. It's slow, right? It's actually pretty fast to go to finance.yahoo.com and get a quote, but it's probably slower than you'd want it to be. Maybe it's unavailable. Maybe Yahoo goes down, right? They're trying to fix the heartbleed bug. You can't run your tests that day. That's no good. So the question should be, for your code, assuming Yahoo is working, does my code work? And the challenge now is, how do we get Yahoo out of the picture? Right? How do we remove that dependency on that server so that we can just be talking about the piece of code we actually care about? We don't want to test all of yahoo.com. We want to test our code. One way to do it is to have a fake implementation of current prices. So here's a test that we derive from test case as always, and I'm going to have a method in here called fake current prices. Now if you remember from our product code, current prices simply returns a dictionary with the keys are the names of stocks and the values of the prices. And this is going to be a fake implementation of it that just returns some canned data. And in my setup, I'm going to make a portfolio, I'm going to buy some stocks, and then I'm going to actually monkey patch the portfolio to change its current prices method into my function. And this works. So this is a little odd, and if you haven't dug really deep into Python internals, you may be surprised to see that you can just replace methods like this on objects, but it works. And now when we run our test and we look at self.p.value, it will actually call self.p.currentPrices, which is our method, fake current prices, which will return that fixed dictionary, and we haven't made any network calls. And we can assert that the value is what we know it's going to be because we know what lies we told about the current price of IBM and HP stock. So good, the test results are predictable. The bad thing is that there's some code that isn't tested. So here I've used the coverage tool, which is a way of measuring what lines of code get executed when you run your tests. It's a way of testing your tests. The theory of your tests is that they're testing all the code you have. How do you know? You run coverage, it tells you which lines of code you haven't actually run under your tests. And here we can see that lines 53 through 56 have not been executed, and 53 through 56 are exactly the lines of code we tried to snip out of the system, which were the lines of code that talked to yahoo.com. But this is code we wrote. We need to test this code somehow, right? So we've got a good system here, but it doesn't test all our code. So we can try faking urllib.urlopen instead. So here what we do is we make a new object that's going to be a stand-in for urllib for us, and it's got a method on it called urlopen. And in our setup, we're going to save away, we're going to jump right into the portfolio 3 module, which is our product code, and it has a reference to urllib. We're going to save that away in our setup. We're going to make an instance of our fake urllib and monkey patch it into our product module. And now, in our product module, urllib refers to our class, and therefore urllib.urlopen refers to our method, and when it gets called, it's going to return the data that we want. Up here, this urllib is returning a file-like object, which returns exactly the CSV data that Yahoo would have returned. I know the details here. Don't worry about the details about the CSV and all that stuff. There's no way to keep up with me right now. Just keep in mind, the idea here is to make an object that works exactly like the component you don't want in your system anymore and put it in place so that the product code will actually call your code instead of that code. And by the time we get down here and we call self.p.value, value calls our current prices module function. Our current prices function calls urllib.urlopen, which it thinks is a standard library module that talks over the network, but is in fact our fake object that we put in place. It gets back that file object, it parses the CSV, it makes the dictionary, it computes the value, and then we get what we want. And by the way, at the end, the teardown method is going to restore the real urllib. It's going to unmonkey patch things. Now, all of our code is executed, right? We've got 100% test coverage. All of our code is executed. The standard lib is stubbed out, and we've made no web access during our tests. So this is really good. The thing that's not so great is we've had to do a lot of sort of handcrafting of engineering there. There's an even better way to do this, which is a thing called mock objects. Mock objects are these amazing things that are, I call them automatic chameleons. They will act like anything you want them to act like. Here's an example where from mock, I import the mock class, and I make a thing called func, which is a mock, and all I say about it is the return value should be the string hello. and then I call it as if it were a function, and it returns hello. Right? It just said, I'll return that, sure, you told me to return that, that's fine. And by the way, the 17 and the something, it just stored them away, and later I can look at that and say, func, what were you called with? And it says, oh, I got called with 17 and something. So this is great. This is perfect for putting in place as a fake object. And it's really easy to do because the mock library also has a patch context manager. So here what we can do is we can say to the mock library, I want you to mock out urllib.urlopen and give me the mock object that you made. And then down here what we say is, I'm going to make urlopen have a return value of this fake Yahoo data. And now when I call self.p.value, it goes through all of our code. It gets to urllib.open, which hits the mock, which gets the return value that we gave it, and it gets back that data, and it comes back up and gives me the value you want. And now, by the way, down here, I can say to urlopen, I assert that you were called with these values. Because, by the way, in our previous example, we didn't actually look at what our fake object got called with. Maybe the URL got broken in some refactoring, and the actual code would have failed where our mock would have succeeded. Here we can actually assert that we're getting called with the URL we thought we were being called with. So now we've got mocking with no explicit setup. We didn't have to write an implementation of something. We simply had to make one out of this magic mock module and tell it what we wanted it to do. The overarching term for all these things is test doubles, which is kind of like stunt doubles in a movie. It's you take the star out and you put in some guy that you don't care about as much and let him do the hard work. So this is very powerful. It isolates our code. Right? We've removed dependencies and focused it more in on smaller code. It focuses our tests, and it removes speed bumps and randomness. A lot of times you'll do this approach not because it's not your code and you want to get it out, but just because that code is slow. The problem is it makes your tests fragile. If you think about what we did, the only reason our mocking worked is because we knew that the product code was calling urllib.urlopen. If someone refactors that product code to use the requests library instead, these tests will all fail. And, by the way, the product code will now be running out to yahoo.com to take a long time before it fails. So we'll have lost all of the benefit. So the only reason we could mock this stuff is because we knew enough about the implementation that we knew exactly how it worked inside. And that's a dangerous situation to be in. Also, by the way, there's another way to do this called dependency injection, which you should look into. So there are too many things. We can't talk about them all. Testing is a big topic, but I wanted to give you pointers and plant some words in your head about some other things. Add cleanup as a method on unittest.testCase objects, which is a nicer way to do things than teardown. Doctest is another thing you'll hear about in the standard library. Only use it for testing code that's already in your docs. If I hear about any one of you using doctest for anything else, I'm going to be mad because we've spent a lot of time here together, and I expect you to listen to me. Nose and py.test are better test runners than unittest. They have a lot of cool features like plugins. DDT is a library that lets you do data-driven tests. So if you have one test method, but you want to have 10 test cases out of it because of these different data, it will do that for you. Coverage is a really awesome thing, and you should use it. Selenium is the tool you'd use for in-browser testing. Jenkins and Travis are continuous integration servers, which are a way of having a place that you can push your code in. It just runs your tests every time you make a change. Other topics. TDD is writing tests before code, which is very interesting. BDD is a way of writing tests in a way that your business people can perhaps write your tests and focus on external behavior. Integration tests get at larger chunks of code, which is a way of testing more realistic scenarios in your product. Load testing tells you about whether you have enough capacity for your traffic, and lots of other topics, I'm sure. So, summing up, how do we do? We've learned that testing is complicated, it's important, but it's worthy, and it's rewarding. Remember the two developers we had at the beginning of the talks? We wanted them to be happy and confident. Here they are. If you think testing is hard, these drawings, the two original drawings, were drawn by my 16-year-old son. If you think testing is hard, try getting a 16-year-old to draw you a third picture. Any questions? How much time do we have for questions? About 5 minutes?
Thank you for your talk. What happens if finance CIO returns JSON instead of CSV?
If Yahoo returns a gzip?
JSON instead of CSV.
Oh, well then that API has changed, and your code is going to have to change.
Okay, so
Right.
tests are going to pass, but the application is going to fail.
Right, exactly. So that's one of the failures of the mock, right, is that we're assuming that we understand the interface to that mocked component well enough that we can replace it. And if that mocked component changes, in this case, our product would also change, so we're going to have to fix it either way. But yeah, there could be scenarios where it changes in a way that your product code would have been okay with, but your test is now mimicking the old behavior, and you've lost track of that. That's one of the ways that mocks are really dangerous. Yeah.
Thanks for the talk. One of the things that I've run into as a barrier to get in is just into testing is getting all the pieces together and in the right place. So a little bit of blatant self-promotion. I've made a GitHub repo that has a Python unit test skeleton with dashes between them. You can search for it. That has a bunch of kind of boilerplate code you can take to get up to speed much more quickly.
Great.
So I find that super helpful to make the burden of getting into testing as small as possible.
Fabulous.
Thanks.
Python unit test skeleton? Great.
Hi. So when I'm aiming for 100% coverage, I often have trouble with the main method. Do you have any advice on testing that?
Make your main, well, first of all, if dunder name equals dunder main,
Yeah.
you should have one line of code in there, which should be sys.exit of main of sys.argv. And then your main function is now a pure function that takes a list of arguments and returns a status code. And you can test that, right? That just takes arguments and it takes a return value. And then all of your connection to the external world happens in that one line in your dunder name, dunder main. And it's hard to mess up that line, so you can just leave that alone. Okay. That's my advice.
Cool, thanks.
Two questions. I've heard it said that dry doesn't apply to testing, but when I see my coworker just cut and paste one test to the next, and I go back and something changes with the test, it feels like it should be dry.
That's silly, yeah. I have no idea why people would say that dry shouldn't apply to testing. Testing is one of those mysterious worlds where you will find experts and they will say things to you. Not me, I can be trusted, but there'll be other ones who will say these mysterious things and you will believe them because testing is mysterious, but maybe they're wrong.
Well, I mean, in one case where it makes sense to me is that once you start making your tests dry, your tests become more complex, and then don't you have to test your tests?
Yeah, you do.
So
right,
just
but
testing all the way down?
Yeah, so I know why some of why they say they should be dry, because some people like tests as sort of almost documentation of how things should work, and they like a test case to be completely self-contained. But if that means that you have the same 10 lines setting up the same fixture that you're going to use in 60 tests, that just seems silly to me.
Okay. And in the second part, I still have problems with my reusable test data. So I put some of it in the setup, I put some of it in the individual tests, and a little bit in fixtures, which I see a lot of bad talk about fixtures, and I experience that sometimes. So any advice on where to put your reusable test data?
It's really going to depend. I mean, like I said, testing is real engineering, right? If I were up here talking about web performance, people wouldn't say to me, so what should I do to make my website fast, right? Everyone knows that making websites fast is like serious work where you have to really consider all these complicated factors. Testing's exactly the same. I don't know what your test data is or where, I can't answer that question. We're going to have to sit down and really think about what problems you're facing and what the best solutions are. In a well-tested system, it's not unusual to have more lines of tests than you have of product. And why wouldn't that code be rich and complex and have thorny problems that you're not sure you solved the right way and you're going to have to go back and refactor, et cetera, et cetera? It's engineering. Yeah.
Okay, so JSON fixtures, that's always going to be there.
Yeah, that sounds great.
Hi, I have a pretty essential question. You said that it's a good idea to reduce some of the modules that you're testing, like if you've got 8 that are all feeding into one test. Do you just mean to just stow the code somewhere else briefly and throw a pass in there so it'll just go through it? Or?
No,
okay.
and the reason why is because that makes your tests hard to run, right? You don't want to have to edit your product code before you can run your tests. You need to have an automated test that you can run with the push of a button. Some people have it happen automatically when they save a file in their editor. Every time their Control-S twitch comes in,
Like
the
Jenkins?
tests all run. Like what?
Like Jenkins or Travis that you were talking about?
No, even more than that. Every time literally the file hits the disk, their tests run. So you want your tests to go as quickly as possible and as automatically as possible. So when I say removing code, I mean engineer the tests so that it reconfigures the system and finds just the code that it wants to test.
Thank you.
The session runner went away, so we're going to be here all afternoon.
This was a very good talk. Thank you very much. I saw a recording of a talk you gave a few years ago, also on testing.
Yes.
You brought in the issue of testing the missile silo.
Yeah.
What have you learned in the last few years about testing?
What have I learned? I have learned, if anything, I've learned that it is even more complicated than I thought it was before. That as your system gets complex, the tests seem to get complex faster than the system gets complex. And that the more work you can put into attacking that problem early, the better off you're going to be. And I've learned about the downsides of mocking.
Thank you.
Sure. Okay.
Thanks for the great talk, and thank you for the permission to refactor tests and to test tests.
Yes.
I got to try that as soon as possible.
Yes.
My question is, I've been starting to do unit testing and stuff, and suddenly I've been forced into dependency injection land. And so I wonder if you had any thoughts on mix-ins, since we're in Python land here and we can have multiple inheritance, versus dependency injection, and if you have any global thoughts on that whole concept.
Well, so dependency injection, for people who haven't encountered the term, means that the things you depend on, like urllib.urlopen that we used in the product code, instead of it being an explicit reference to a module that we would monkey patch by name, it would be a thing passed in explicitly into the portfolio class on construction. So the portfolio class, when it was constructed, would know when I need to talk to the network, I have been given this thing, and it's the thing I will use to talk to the network. And that means that when you do your tests, instead of doing weird monkey patching, you can just pass in a different thing, and you default it to url.urlopen so that your real callers don't have to think about it. The downside of dependency injection is that you're cluttering up the signatures of your methods with all sorts of weird stuff that starts with an underscore, and the doc says don't ever use this, and weird stuff like that. That's unfortunate. And by the way, it's hard to even get all of them, and in a big system you don't want 100 dependency injections.
Yeah, exactly.
Mix-ins, I'm not sure how you'd use mix-ins for that, because mix-ins are things that give you flexibility at the time you define a class, but that means you'd have to define a different product class to get a mix-in that has different dependencies. So I guess we'd have to talk about how a mix-in could solve that, and maybe you can teach me something about it, because I haven't encountered that as a way to solve the dependency problem for during tests.
Well, for instance, you have your hierarchy of the thing you're doing, and then you just mix in urllib with it.
I see. But how do you get it out of it? That's the thing. The thing that you've derived from both your product code and urllib, now is the thing that you need to test. Or are you deriving a different thing that mixes in something else? In which case you're creating new...
You're creating another... Right.
Right. So that's another way to do it. Right. Yeah. You could define a new class in your test, which is your product code mixed in with the dependencies.
Yes.
That sounds cool.
Yeah. That's fun.
See, you learn something when you do PyCon talks. There's no one over there. Go.
All right, it's me, Ned.
Oh, hi, it's the runner. He came back.
So we're out of time, but I'd like to thank you.
Thank you.
For a great talk, and thank you to all our questions.